Welcome back to Math 104. We see that our experiment of rolling two dice has 36 outcomes, and they are equally likely outcomes because we assumed that the dice were fair. Why 36? We can count them, or we can notice that they fall into a 6 by 6 array. So there are 6 times 6 items in this table. To find the probability of E intersect F, we are simply counting up how many outcomes are in both events, and there are 3 of them, 2, 2, 2, 4, and 2, 6. So the probability of E intersect F is 3 out of 36. For E intersect G, there are 4 outcomes in common, 4, 6, 5, 5, 6, 4, and 6, 6. So the probability of E intersect G equals 4 over 36. And finally, the probability of F intersect G, that's the easiest of all, that equals 0, or 0 out of 36. But we can just write 0, because there is no overlap. There are no outcomes in common. If the red die shows a 2, there's no way that the green die could have a large enough number on it that the sum would be 9 or greater. Having figured out the intersections, it is easy to answer the next question, which pairs of events, if any, are mutually exclusive. F and G are mutually exclusive. They have no outcomes in common. They cannot both occur on the same roll of the dice. As a follow-up question, what do you notice about probability of F union G in relation to probability of F and probability of G? We find the probability of F union G by finding how many outcomes are in F, or in G, or in both. There are 16 total outcomes that fit that description. F itself contains 6 outcomes, and G itself contains 10 outcomes. Well, that's interesting because the addition rule said that the probability of F union G should equal the probability of F plus the probability of G minus the probability of the intersection of F and G. But there is nothing in the intersection here. This minus probability of F intersect G is irrelevant, and sure enough, the probability of this union really is just the sum of the separate probabilities. Why is that important? This is actually a key point. Since F and G are mutually exclusive events, the addition rule simplifies to just probability of the union equals probability of F plus probability of G. That's it. That's not just true of these mutually exclusive events, that's true of any pair of mutually exclusive events. Let's do a comprehension check before we continue. Can two events be complementary, but not mutually exclusive? Think what the words mean. Can two events be complementary, but not mutually exclusive? No, they cannot. If two events are complementary, then one is the opposite of the other, so they cannot both occur. We can write that E intersect its complements equals the null set. There's nothing there. So E and its complements must be mutually exclusive. The answer here is a big no. How about the other way? Can two events be mutually exclusive but not complementary? Yes, they can. To help see this, consider the event H, that the red die shows a 3. If the red die shows a 3, well, it's certainly the case that it can't also show a 2. That means the intersection of the red die shows a 2 with the red die shows a 3 is empty. There are no outcomes there. But it is not the case that F and H are complementary. On the contrary, F and H are not complementary. They are not opposites of one another. It is not the case that when you roll the dice, either F happens or H happens. The conclusion is that two events such as F and H can be mutually exclusive, but not complementary. We have a few more observations to make about probabilities of unions, intersections, and complements. To work up to them, let's look at a new example. At a blood drive, a donor walks in and is tested for blood type. Consider the events O, that the donor has type O blood, and the event N, that the donor has a negative blood type. To understand this, note that in the most common system of classifying blood types, each blood type is in one of the groups O, A, B, or AB, so that our randomly selected donor's blood will be in one of those 4 groups. Moreover, that donor's blood will be either positive or negative, depending on whether it has the so-called Rh factor. This means that there are actually 8 distinct blood types, and each donor will be identified at the blood drive as having one of these 8 types. When we analyze in terms of a Venn diagram, we have a circle for the event O and another circle for the event N. There is only one blood type in the intersection, and that's O negative. There is only one blood type in this region, inside the O circle and outside the N circle, and that's O positive. There are several negative blood types that are not type O, namely A negative, B negative, and AB negative, and all the rest live in this outside region, A positive, B positive, and AB positive. These are the types that are not type O, and they're not negative, which means that they are positive. So what's the issue here? What's the catch? The issue is that, in general, a patient who needs a blood transfusion cannot just receive blood from anyone. Instead, the patient's blood type needs to be compatible with the donor's blood type. So what does compatible mean? Compatibility requires 2 things. One is related to the letter, and the other is related to positive versus negative. As far as just the letters go, patients with certain letter types can receive from donors with certain letter types, but there are restrictions. So type O can receive only from type O. Type AB can receive from anybody, if we forget for the moment about positive versus negative. As far as positive versus negative goes, if you have a positive blood type, you can receive positive or negative blood, whereas if you have a negative blood type, you can receive only from a donor who has a negative type. Why then have we singled out the events O and N, having type O blood and having a negative blood type? We've singled them out because from the point of view of the people running the blood drive, if the randomly selected donor has type O blood, that's very good news. Type O can donate to anyone. If the randomly selected donor has a negative blood type, that's also good news because negative blood types can be given to anyone, apart from the issue of the letter. What if the donor has O negative blood? Well, that's very, very good news because O negative blood can truly be given to any patient. In fact, if you have O negative blood, please donate as often as you can. They'll probably put a faucet in your arm. Every 8 weeks, they can just turn on the faucet and take a pint of blood for you. It's a very good deed that you can perform. What do we know about the probabilities? These numbers are for the United States population only. They are not true everywhere. 45% of the United States population has type O blood, 16% have some kind of negative blood type, and 7% have O negative blood. Let's label each of the 4 basic regions of the Venn diagram with its probability and write the event corresponding to that basic region in terms of unions, intersections, and/or complements. Let's notice that the only number that's been given here, which is the probability of a single basic region, is this last one, the 7% chance that our randomly selected donor has type O negative blood. That's a 0.07 probability that gets written into this overlap region. And now the moment of truth. This is where many students make mistakes. This 45%, this 0.45 probability that our randomly selected donor has type O blood, does not refer to a single basic region. Instead, it refers to the entire O circle. That means that the probabilities in these 2 basic regions combined must add up to 0.45. And that means that the probability in this region equals 0.38. So to be clear, that was 0.45 minus the 7% that have already been accounted for. So after accounting for the 7% of donors who are O negative, that leaves 38% who are O positive. Now, how do we write these regions in terms of unions, intersections, and complements? We just found that the probability of O intersect N equals 0.07. That's the region in the middle here, O intersect N. What about this region? Inside the O circle, but outside the N circle. That region can be written as O intersect N complement. Inside the O circle and outside the N circle. Intersection translates the word and. Complement translates the word not, or outside of. If the word or were relevant here, we would have a use for unions, but it isn't. We're talking about one basic region. The blood is type O, and it's not negative. That probability we found was 0.38. Before going on to the next video, carry out the same process for the other two basic regions of the Venn diagram. That is, for each of the other regions, find the probability of that region and write that region in terms of unions, intersections, and complements.